Welcome to today's explainer. We rely on our computers for absolute, unquestionable precision. But what if I told you that every single data format inside that machine is actually a carefully calculated compromise? Today, we're enthusiastically diving into the fascinating world of computer memory to unpack a fundamental limitation of computing, the accuracy versus range trade-off.
Let's say you type a super simple math problem, like 0.1 plus 0.2, into certain computer interpreters. You might be totally shocked to see the output, 0.30000000001. No way, right? So why would a highly advanced computer, a machine literally built to crunch numbers, fail at basic primary school math? Well, the answer lies in how it physically stores numbers, and it's a mystery we're going to solve right now.
Okay, let's dive into this. Think of this as our investigative roadmap. We'll quickly cover the floating point problem, mantissa and exponent, the need for normalization, the big accuracy versus range trade, and finally, the real-world consequences of these binary limits.
All right, Section 1, the floating point problem, why finite resources create imperfect math. So to really understand this bizarre bug, we have to establish one absolutely undeniable reality. Computer memory is not infinite. A system only has a fixed, finite number of bits to represent data. And because of this fixed length, it simply cannot store every conceivable number with absolute perfection. It just can't. When we're dealing with real numbers with fractional parts, binary representations are sometimes only a very close approximation. That completely bizarre output of 0.3001, that happens because it's physically impossible for the computer to store all fractions with the exact precision we expect from our everyday decimal system. Moving right along to Section 2, mantissa and exponent explained, basically the two heroes of floating point data. Now these two components, they act kind of like two teams playing tug-of-war on a rope, fighting over limited space. The mantissa represents the decimal or fractional part of the binary representation, while the exponent is the power to which the base number is raised. Think of it like a slider. Since there's a fixed total number of bits available in the system, these two have to share that space. Give a few bits to the mantissa, and you literally have to steal them away from the exponent. If we look under the hood, binary numbers represent fractions based strictly on powers of 2. So binary place values are broken down into halves, quarters, eighths, sixteenths, you get the idea. A binary 0.1 is exactly 1/2, or 0.5 in decimal. A binary 0.01 is a quarter, or 0.25. The computer actually has to piece together every single fractional number you give it by adding up these specific, rigid binary fractions. Which brings us to Section 3, the need for normalization. Maximizing limited digital space. Look, because digital space is at such a huge premium, computers use this really strict rule called normalized form to make sure not a single bit is wasted. Before we tackle the big trade-off, we gotta understand this. Basically, the binary point is adjusted so that a positive mantissa always starts with 0, 1, and a negative mantissa in 2's complement starts with 1, 0. The core rule here is that those first two digits of the mantissa must always be different. So why jump through all these hoops? Well, normalization minimizes the number of leading zeros, meaning we aren't wasting precious memory storing empty space. It avoids the chaos of a single number having multiple different binary representations. And above all, it maximizes the potential range and precision, preserving the maximum possible accuracy for a given number of bits. Essentially, the system is desperately trying to be as accurate as it possibly can within its physical constraints. All right, Section 4, accuracy versus range trade. The ultimate architectural dilemma. So the crucial point is right here. This is the epicenter of our whole dilemma. We know space is limited, and we know data is normalized. But how do we actually divide the bits between the mantissa and exponent? It's a total zero-sum game. Giving more bits to the mantissa gives you greater accuracy, because you're keeping more digits in the fractional part. But because you took those bits away from the exponent, you completely crush the range of values the system can handle. Conversely, throw more bits at the exponent, and you get a massive range of extremely large or extremely small numbers, but your accuracy drops significantly. Let's put this into perspective. Imagine we have exactly 16 total bits to allocate. In step 1, let's say we give a generous 12 bits to the mantissa, leaving only 4 bits for the exponent. Wow, our numbers will be highly accurate. But a 4-bit 2's complement exponent can only represent a tiny range of powers, specifically from -8 to +7. So the numbers we can store are incredibly precise, but we just can't store very big ones. Now look at step 2. We shift the slider. We allocate 8 bits for the mantissa and 8 for the exponent. Suddenly, our exponent can reach massive numbers, expanding our range exponentially. But because our mantissa shrank down to 8 bits, our precision takes a massive hit. It's a true trade-off. You absolutely cannot have both. You just have to choose. And finally, Section 5, Consequences of Binary Limits, the Real-World Fallout. Okay, let's look at the real-world fallout of this delicate balancing act and finally solve that math bug from the very beginning. Remember how we said binary fractions are made entirely of halves, quarters, and eighths? Well, what happens when you try to store the decimal fraction 0.20 or even 0.1? The truth is, they literally cannot be represented exactly within these binary constraints. The closest you might get to 0.20 with limited bits is 0.25 or maybe 0.1875. This fixed length means it isn't possible to store all fractions precisely. The system simply gets as close as it possibly can. So when you casually ask a computer to add 0.1 and 0.2, it's actually adding two very slightly imprecise binary approximations together. And that tiny imprecision spills over into that unexpected trailing 1 at the very end of our decimal.
So what does this mean in practice? Well, when the mantissa doesn't have enough bits to store the whole binary number, precision is lost. It just gets truncated. And that inevitably leads to rounding errors during arithmetic. Furthermore, if you calculate a number that's just too large for your chosen exponent bits, you get what's called overflow. On the flip side, if a result is too small to be precisely represented in the available system, you get underflow. Literally every choice a developer makes about bit allocation carries these heavy, real-world consequences.
Which leaves us with a pretty fascinating question to ponder. We trust our computers with literally everything, right? Our banking, our engineering, our science, the whole shebang. But if, at the absolute lowest level, our machines rely on finite bits restricted by this accuracy versus range trade-off, is all digital precision ultimately just a carefully chosen approximation? It's kind of wild to think about. It's a brilliant reminder that even our most perfect, advanced machines are fundamentally bound by the physical limits of the space we give them.